Professor for the. So, hi everyone. Thank you for attending this talk. So I feel really honored to give my research presentation titled on adaptive robust evidential optimization for open set detection from imbalanced data. So like Professor said, I am Hitesh Sapkota, PhD candidate in Rochester Institute of Technology. I'm also the active member of machine learning and data intensive computing research lab led by my advisor, Professor Ziu. Let's get started. So first I'm going to introduce the idea of the open set detection. And then like we can see what are the problems like under the open set detection in the imbalance classification setting. After that, I'll formally kind of introduce our adaptive robust evidential optimization technique. And then we talk in detail about the experimental result. And finally, I'll conclude the talk. So before going into the open set detection, let's try to understand what the deep learning is doing, right? So, I mean, if we talk about the machine learning or deep learning technique, right? So, I mean, it consists of, I think, basically two phases, training phase and testing phase. So during the training phase, so if we talk about the, deep learning, then that is nothing other than, learning a series of projection metrics to map the given input to the output, right? So in other words, so like deep learning technique tries to map the given input to the output using some loss such as cross entropy loss, right? And then to update the neural network works, we can use the different optimizers, for instance, stochastic gradient descent and so on. So let's look at to that picture, right? So we have the bunch of images related to cat and also the bunch of images related to the dog. So here during the training process, what the deep learning technique is trying to do is that it's just trying to learn the different projection metrics so that given the image, it can map to either to the cat class or dog class, right? So that means essentially it's just like learning some like kind of mapping function by using the different words associated with the deep neural network. So once we do the training, so next phase is called testing, right? So during the testing, we pass the new image like through a series of projection metrics that we learn during the training process to get the final prediction. So for instance, let's say if we pass the image of, let's say, dog, then like we can get the probability of given image being dog and also probability of given image as cat, right? So here just for the illustrative purpose, we can see that probability of like image being dog is 99%, whereas the probability of cat is 1%, right? Now let's try to be more curious, right? So what happens when we pass the image of the, let's say, tiger through the model that is trained like to classify dog and cat? Okay, now let's try to pass this image, right? So now like if we pass through the deep neural network, then it may be possible that the given image is incorrectly classified to the cat class with high kind of confidence score. So in this case, you can say that, okay, with 90% probability, the model may say that I think that this image belongs to cat category because of the some type of text or similarity that exists between cat class and the tiger class. That's why, I mean, now it kind of motivates us to the point that we used to have some type of model, right? So that can understand that kind of understands that it's not shameful to say that I do not know, instead of being wrong in a harmful way. So that means there is nothing wrong saying I don't know. So in this case, ideally we would want the model to say I don't know instead of wrongly classifying to the cat class. So that what we want, and this notion is called open set detection, right? So that means during the testing phase we have some image, right? So from the class that is not seen during the training phase, and we want the model to say I don't know in that image. So now I mean, we just wanted to be curious, right? What happens when we pass the new image, right, from the different class? So the question is whether it's important to consider this open set problem, right, seriously. So the answer is yes. I think it's very critical, right? Especially if we, let's say, consider the domain like medicine, autonomous driving, public safety, or different type of military operations, right? There, I think the detecting the unknown image is very critical. For instance, let's consider one example from the medical domain, right? Let's say I need to detect given image whether that has some cancerous tissue or not, right? So in that case, I think it's safer to say I don't know, right? I mean, instead of saying that the image doesn't contain any cancerous tissue, because if it says that, then I think it's a matter of life of someone, right? So in that case, if the model says that I don't know, then we can involve the human in the loop to investigate it further. So now the question is, how do we quantify this uncertainty, right? Or the probability of the given sample being open set, right? So that means, how do we quantify this uncertainty so that the model can say I don't know whenever there is new image? So if we look at the existing literature, so there are a bunch of work that tries to quantify the uncertainty. So some of the representative works are listed here. For instance, deep ensemble, or Bayesian neural network, or OpenMax, and variance and evidential learning, right? So let's try to briefly get the idea of the deep ensemble, right? So in the deep ensemble, so we can learn the different base learner, right? And the variation on those base learner can be either through the training them by the subset of the data. For instance, base learner 1 can be trained using subset of data 1, and then base learner 2 by subset of data 2, or something like that, right? Or we can get the variation by randomly initializing the input words, right? And then during the testing phase, so we can collect the multiple base learners output, right? And the variance associated with that output can be used as kind of proxy to say whether given sample is open set sample or not, right? So usually if we have high uncertainty, then we would expect the kind of given sample from the open set, right? Or from the out of distribution. So but the problem is that if we try to look at the deep learning, right, like deep neural network, right, it's kind of heavily over parameterized. That's why instead of getting the the different output, the each of the base learner can provide the similar type of output, resulting into low uncertainty, right, or low variance. So that means even if we pass the unknown image because of this over parameterization, or because of this overfitting, the model, I mean, each of the base model wrongly can say is kind of in distribution. So that way we may not be able to get too much kind of valuable information from the base learners. So that is the problem with deep ensemble, right? So there similar, there is Bayesian neural network, right? So idea is that we are going to define the distribution for each weight in the neural network, and then during the output, because of that distribution, we may get some type of variation. So that means the in terms of the uncertainty score. Again, I think this is the promising, I think, the direction, but it's going to be very computationally expensive, right? Because we have to define the distribution for each weight, and then doing the inference process is very expensive. So another direction is OpenMax and its variants. So OpenMax, we can think this as kind of post-processing step, right? So that means first we train some deep neural network, and then once we are done with the training, then in the output side we add one more node. So that node indicates the probability of the given sample being uncertain. So that means, let's say if I have, let's say, C class, right? Let's say if I have 10 class, then during the training, so my output nodes will be 10. And then once we are done with the training, after that, during the post-processing step, we kind of renormalize the output to the 11 nodes, so that the 11th node is going to say the probability of given sample being uncertain. So that is the idea of the OpenMax. But like I said before, right, this is the post-processing step and doesn't have systematic way for uncertainty quantification. So I think the most promising direction from the both computational perspective, as well as from the systematic way of quantifying the uncertainty, I think evidential learning is the one of the promising direction. So basically, in the evidential learning, we quantify the uncertainty in a more systematic way, based on the subjective logic principle. And it's, like I said, it's going to be computationally more cheaper, right? So let's look at how do we do the kind of training in this evidential learning. So in the evidential learning, we are going to have some evidential model. And this model learns to form the opinion for each class samples through the belief score, right? And the output mass or output score is going to be distributed to two different sections. One is belief and second one is the uncertainty. So for instance, in this figure we have the let's say image of the cat, right? So in that case, so in the output, so we get the evidence of the given image being cat, and also evidence of given like a kind of image being dog, right? So in addition to that, so once we get the evidence here, and then we can also get the belief of the given image as cat, right, which is, let's say, 80%, and also belief of the given as dog, which is 10%. So in addition to that, we can also have like uncertainty score, right? So that means let's say I have the uncertainty score equals to 10%, right? So that way like we have the like mass is distributed to belief score plus uncertainty score. And in this case, so during the training phase, we can have evidential loss, right? For instance, one example is mean square error based evidential loss. So if we look to the equation 1, so we can see, right? So during the training process, so it's going to kind of increase the evidence for the correct class while being being kind of so it kind of tries to increase the evidence for correct class, whereas for the other class it's not going to increase the evidence. So for instance, in this example, so we have the like cat image, right? So in that case, the loss encourages the evidence of the given sample being cat, like it's going to increase that evidence, whereas not increasing the evidence of being dog or uncertainty, right? So that way I think it's going to learn, right? So that means in the evidential we have explicit kind of uncertainty score, to say I don't know. Now what happens is that during the testing, let's say if I pass the image of the tiger, then now output is going to be distributed to belief of given sample as cat, belief of given sample as dog, and the uncertainty score. Now, since the model hasn't kind of trained to build the kind of belief score for this type of image, right? Because this is cat, that's why it can provide the high uncertainty score in this image, meaning that the model thinks that this is the open set sample. So so now it looks like we are being able to solve the open set detection, right, just by using the evidential learning. But now let's see more challenging case, right? So now let's see like open set detection under imbalanced data. So for this, let's look at a figure, right? So in the figure, let's say we have some species classification problem, right? So where let's say I need to classify the given image to aquatic mammals or the fish related class, right? Now let's see here, I have two modes. So meaning that within the aquatic mammals class, so I have two different groups, right? One is whales and another one is dolphin, right? And let's consider that under the whales group we have many like images, and it's more relatively easier to learn, right? And then let's say second class, this dolphin, right, where we have very few samples. So I mean, both of them belong to the aquatic mammals, but we have two different groups within the class, right? One group with very few difficult samples, and also they are very limited, right? And also within the class fish, we have very few samples compared to, let's say, whales category, right? Now, what happens when we train the evidential like kind of model, right? So in that case, like it kind of learns to form the opinion or belief to the whales like kind of group, right? While because of the limited samples or because of the difficulty of the sample, it doesn't learn to form the like kind of evidence for, let's say, dolphin group or even the fish class, right? So during now let's think that we are done with the training, right? Now during the testing, let's say we pass the image related to dolphin and fish, right? So since it doesn't have too much evidence for those, then it may just say that I don't know those samples. I haven't seen those type of samples during the training process, and may classify those kind of images as the open set samples. So that is wrong, right? Because they are actually like the samples from the classes that we have seen during the training process. So now we see that simple evidential model learning is not going to work, right? So now let's try to seek the solution for this. So how do we tackle this problem? So that's why there is the title called open set detection under imbalanced class, right? Where we have the one class with very few samples, and also within the same class I can have multiple groups. One group easy and the second group can be difficult, right? Now let's think about the solution, right? So I think most straightforward solution would be, why don't we oversample sample the in the minority classes, right? So that means let's try to increase the number of samples in the minority class using some technique like smoothing, right? So in that case, the problem is that so the oversampling is going to ignore this type of like group, right? Because we don't have group level annotation, so we can do sampling only based on the class, right? So as a result of that, the model may still be able to make the like incorrect, or may think that the images corresponding to this group as the open set samples, which is wrong. So it's kind of tries to partially solve, but I mean it's not going to work. So this is the first technique that we can think, right? And the second technique that we can think to solve this problem is distributionally robust optimization. Or we can distributionally robust optimization can be abbreviated as DRO. So this provides the more effective way to handle the imbalanced class as well as the difficult samples, right? So how to do that? So let's try to look at the question 3, right? So let's say that I have total n total number of data points, right? And ln is the kind of loss associated with the nth data sample, and theta is the neural network or deep neural network parameter or evidential model parameter, right? And P1 is the weight associated with the nth data sample. So P1 tells how much emphasis that I want to give to the nth data point, right? And we want to actually find the worst worst case loss, right? By doing maximization with respect to this P. So P is n-dimensional vector, and this weight, so this weight is going to be defined by the uncertainty set that is defined in the equation 4, right? So that means sum of the weight for the nth data sample is going to be 1, and each weight is going to be non-negative, and also there is going to be this constraint, right? So measuring the distance between the distribution that I want to find and the uniform distribution, right? And this is going to be constrained by the hyperparameter called eta. So this is the overall DRO framework, right? So that means under the DRO framework, we want to find the optimized weight, so that we can give more emphasis on the difficult data samples. Now let's try to visualize this framework, right? So DRO framework, so we can think the DRO framework as some type of ball, right? With the center that is given by the uniform distribution. And this eta parameter, this is the radius of the ball. So that defines the uncertainty set under this framework, right? Now, just to understand this if impact of this hyperparameter eta, let's try to consider two extremes, right? So let's say what happens when eta turns to 0. So that means my ball is going to shrink to the the center. So that means the uniform distribution, right? So in that case, so even from this we can look, right? So let's say if eta tends to 0, right? So that means we this doesn't allow the distribution a p distribution from the uniform distribution, right? So that means our ultimate solution is going to be kind of uniform distribution where each p1 is going to be 1 over n, right? So that means here we are going to consider all the data samples equally. So that means weight for each data sample is going to be equal. Now let's look at other extreme, right? What happens when we eta is going to be close to infinity? So in that case, we give full flexibility. for the p distribution, right? So in that case, so if we look here, right, so let's say this is infinity, right? So that means we give full flexibility. So to maximize this under this p, the data sample with the highest score has to take all the weight, right, while being 0 for all of them. So that means P1 is going to be 1 for the most difficult data sample, while this value is going to be 0 for the rest, to maximize this, right? So that's why we can see in the visualization, right? So that means one data sample that is most difficult one based on the loss is going to take all the mass. So this means, so in summary, when eta tends to infinity, so we are just focusing on the most difficult data set, right? And then when the this eta tends to 0, then we just give equal emphasis on the all the data samples. Now let's try to use this, right? So that means let's try to give more emphasis on the difficult data samples using this DRO framework. So the problem is that, so if we constantly focus on the difficult data samples throughout the training, then it's not going to learn well from the even the simpler data set. That kind of loses the generalization ability. And also, since it's going to focus too much on the difficult data samples, so it may just completely ignore the data sample from the minority class, right? As a result of that, during the testing phase, so whenever there is simple kind of sample from the easy kind of class, right? So let's say from the Wells group, so in that case it may just say that I don't know, or from the minority class it just say I don't know, right? So that is again going to be problematic. So just in the summary, right, if we do just oversampling, it's going to completely ignore the difficult samples. And if we just use the DRO, then it may lose the generalization ability, and at the same time it may just ignore the minority classes. So what is the solution? Now I think the solution lies within the DRO framework. So we have this critical parameter called eta, right, hyperparameter. So the question is whether we can leverage that eta parameter in the DRO framework to ensure the training from all type of samples, right? So ultimately we want to have good training from easy samples so that it can be generalized well, and then we can also we also want the model to learn well from the minority and difficult data samples, right? That's what we want. So that's where our adaptive robust evidential optimization comes into picture, right? So actually this work is recently published in ICLR 2023. So let's have a detailed look on this. Okay, now the adaptive training framework is like this. So first we are going to give equal emphasis on all the data samples, right? So how do we do that? So by making eta close to 0. So that way it's going to learn the generic representation for all these from most of the data samples. And then during the as training progresses, we are going to increase the eta value so that it's going to focus more on the difficult data samples, right? And ultimately, so we can focus on the most difficult data samples, right? And also this may not ensure the proper learning from minority group, because it mostly cares about the difficult data sample. That's why we also propose some kind of loss that ensures that the model has also learned well from the minority class. So I'll show that detail in the upcoming slides. Now let's try to look at, right, now we say that okay, we can increase the eta value, but how do we increase that, right? So what would be the increase rate for that? So I think this rate of increase of this eta really depends on the kind of nature of data set, right? So let's consider that I have very easy data set. So in that case, the model is not going to take too much time to learn the generic representation. In that case, it's better to quickly focus on the difficult data samples, right? So for that, I think we want higher rate of increase for the eta value versus, let's say, another data set, right, where I have relatively that is difficult ones. There, even to capture the generic representation, it's going to take some time. That's why it's better to stay in the low eta value for a long kind of period of the training, right? And then in the later phase we can just focus on the difficult. That's why, so what we want is that for the easy data set, we want the eta value to increase fast, right? And then for the relatively difficult data set, we want the eta value to, like kind of increase slowly. So that's why we really want this, rate of increase to be adaptive in nature. So for that, so we leverage this function called multi-scheduler function, right? So to change this eta value. So here I have shown some of the examples, right? So we can call those as, atomic basis function. So they are the, just basic component to define the multi-scheduler function. For instance, this is the cosine function, offset cosine function, exponential function, right? And this is multi-scheduler function. This is like the convex combination of the offset and exponential function. Now, this W1 parameter, right? We have different W1 values over here. So depending on the W1 like parameter, so that defines the, how do we want to combine the offset function and exponential, right? So depending on this value, we have different curves, right? So this means we have, more flexibility of changing the eta value depending on the data set. Now the matter is, how do we learn this W value, right? So once we figure out the way to learn this hyperparameter of W value, then I think we can make the, technique adaptive to the nature of the data set. And for this, I think we can leverage the, validation data set to get the optimal like multi-scheduler function depending on the nature of the data set. And we'll have a, detailed look on that in the upcoming slides. That is the idea, right? So in our technique, so we want to learn generic representation. In the later phase, we want to focus on the difficult, right? So how do we realize that? So we can formally define the this adaptive learning technique by using the equation, right? So we have this equation 6. So that looks similar to, DRO framework, right? But if you look to the equation 7, so that is defining the uncertainty for this framework. So we can see that we have this eta t parameter, right? Where t is the, current epoch. Now the eta t value is not going to be constant. Actually, it's going to change as training progresses. So and how we are going to change that is going to be like given by the equation 8, right? So where in the denominator you have this multi-scheduler function with t being the current epoch and capital T being the total number of epoch, right? And then W and beta, so those are the hyperparameter associated with that multi-scheduler function. So like I said before, multi-scheduler function is going to be like kind of non-increasing or decreasing in nature. That's why our eta t is going to be, change as training progresses. So this multi-scheduler function, we can formulate this as convex combination of set of atomic scheduler function, right? So for instance, atomic scheduler function can be cosine, offset cosine, or exponential, right? And we have this constant. So here in this equation, we have total m those type of atomic scheduler function, and we have the constant over this, right? Because this is the, convex combination of those. Now we need to optimize the hyperparameter W and beta associated with this multi-scheduler function, right? So for that, we are going to rely on hypergradient technique for that, or hyperparameter optimization technique, right? So that is the like adaptive learning part, right? Where we want to increase the eta t in a systematic way so that it's going to learn well from all type of samples. Now, this may not, guarantee the proper learning from minority classes. That's why we need to explicitly ensure the learning from the minority classes as well. So for that, like we all again leverage this multi-scheduler function, right? So basically, as the training progresses in the later phase of training, we want to give like equal emphasis on all these classes, irrespective of the number of, data sample for that class, right? So that means like eventually like the weight for each class is going to be 1/c, irrespective of the number of samples. So that way, so we are going to, give more emphasis on the minority class because we have very few samples for the minority classes. So this is called a ratio biased weight augmentation. So we impose this in the later phase of training. Now I think we are also set to go with how do we do training, right? Now we have, hyperparameters associated with that multi-scheduler function. And also we have the parameters for neural network, right? Now we need to like optimize both of them. So this can be achieved through bi-level optimization, where in the inner loop, we optimize the modal parameter called theta by keeping the hyperparameters constant, right? And then in the outer loop, so we optimize the hyperparameter associated with that multi-scheduler function, right? The difference is that when we optimize the neural network parameter, we rely on the training data set. And for the hyperparameter, we rely on the like kind of validation data set, right? So that's the overall, like kind of idea of doing this learning here. Now let's look at like from the algorithm, right? So in our like algorithm, we have this hyperparameter space that is denoted by capital H, right? And then we have P indicating the total number of the kind of models that we do training during the like kind of training phase, right? And S is the kind of number of steps where we do regular evaluation. And then eval is the kind of evaluation metric, and p hat is the number of worst performing kind of model that we want to consider in the algorithm. So we can have a look on detail on that. And t is the total number of epoch, right? So first we consider p total models, right? And for each model, so we initialize the parameter as well as hyperparameter associated with those models, right? And then so and then for certain number of steps, we optimize like kind of parameter associated with each of the base model, right? So I have p total models. And then if I once I reach to the certain number of step indicated by S, then we evaluate each of the model using the evaluation data set. And then I identify the p hat number of worst performing model based on that evaluation accuracy. And then what we do is that since that is doing very bad, right? So that means the hyperparameter that the particular model is considering may not be the good one to find the good solution, right? So that means the probability of having the good solution on that hyperparameter space may be very low, right? That's why next step what we do is that we like replace the parameter of that worst performing model by using the best performing model. Like I can have multiple best performing model, right? Then I can just uniformly select one of that model and then try to like kind of replace the worst performing model parameter by the best performing one. And for the hyperparameter, we can again go to next hyperparameter space, right, by doing some type of exploration, so that we can increase the chance of having the even better performance, right? And then ultimately, so based on the validation data set, we select the best model, right? And then we return that the parameter associated with this best model. So this is the overall training framework of our technique. And also in in terms of theoretical like kind of equivalence, we have shown that our proposed technique is indeed equivalent to AdaBoost. The reason for showing that connection is that now it's it poses different type of benefits. For instance, first is that it's going to be less prone to overfitting. So that means it prevents the model from producing highly confident wrong prediction, and that is going to be very valuable in the open set detection, right? So and also second one is that the optimal function can be regarded, that means the optimal function that we get from this optimization can be regarded as maximizing the L1 geometric margin among the training samples, right? And that actually ensures the good generalization capability, right? Like similar to maximum margin classifier, for instance, SVM, where we try to find out the hyperparameter so that we can like have maximum margin, right? So that actually ensures the better generalization ability. So that helps to improve the cross-set performance actually. So that is the kind of our approach. Now let's look at experimentation, right? So in terms of the experimentation, we have considered 5 different data sets. So CypherTen, Cipher 100, MNIST, ImageNet, and heritage dataset called AHET. So in the Cipher 10, we have total 10 classes in the original data distribution. So we consider the 5 classes as the closed set, and out of those 5 classes, 1 class is made imbalanced by just sampling the subset of data from that class. And the remaining, then for the open set data set, we have considered 2 different settings, right? So in the first setting, we consider 5 remaining classes as the open set from same Cipher 10. And in the second setting, we consider the subset of Cipher 100 called Cipher plus 10 and Cipher plus 50 as open set. So that means I have closed set data set from the 5 classes, right? And then like in terms of open set, one setting is that I have remaining like data set from the remaining 5 classes. In the other case, we have the like the data set from Cipher, like subset of Cipher 100, right? And similarly, in the Cipher 100, we so there are the structure of this superclass, right? So we consider the living being related superclass as the closed set and the remaining as open set, right? So in case of the MNIST data set, we have the, again, we consider the 5 classes as the closed set and the remaining 5 as open set. And also in addition to that, we consider noise, MNIST, and omniglot data set. And in case of this heritage data set, 5 classes we consider as a closed set and 5 classes as open set. So in ImageNet, in the original data set, I think we have the 1,000 total classes, but we just consider the subset of that subset of class from that data set. So and this is the table demonstrating the effectiveness of our technique called AREL compared to other approaches, right? And we measured this open set performance using the mean average precision value, which is higher the better. So EDL is the evidential learning, right? And then this AEDL is the augmented version of this EDL, where we try to oversample the kind of data points from minority class. And DRO is the distribution robust optimization technique, and OpenMax, and so on, right? So if you look at this open set detection performance, we can see that our approach has pretty significant improvement compared to the other baselines. And also we try to visualize the effectiveness of our technique. So the first one is the the distribution of the output in terms of the box plot, right, obtained using EDL, where I don't know whether you can read this, but yeah, first five box plot, they are from the closed set class, and the final one is from the open set class, right? So in the our technique called AREL, we can see that actually the box plot that is under this rectangular red it's a minority class, right? So, and we can see that we have actually good separation between minority class and outlier or the open set. So that kind of demonstrate the effectiveness of our technique. And also we perform some ablation study related to the impact of each scheduler function. So the first indicates only the the performance obtained only using the cosine scheduler function, and second one is only using the exponential function, and third row indicates the performance using both of them, right? So kind of convex combination of both of them. So we can see that there is actually effectiveness of our using this multi-scheduler function. Also, we perform some qualitative analysis to justify the effectiveness of our AREL technique. So if you look at the figure in the left side, so the first row indicates the some of the samples from minority class called POR, right? And the second row, so those are the some of the difficult samples that are from the closed set class. So all of those samples are from the closed set class. And the table shown in the right side, so this each number indicates the ranking of the given sample, right, based on this uncertainty score. So that means low ranking indicates the low uncertainty score or low open set score. So if you compare AREL with EDL, AEDL, and DRO, we have low ranking, right, for board one. So that means it has less uncertainty score. And indeed, those samples are from the closed set class. We want them to have, low uncertainty score, right? That's why we have, low like kind of ranking, right? So compared to the rest. So this also can kind of justifies that our techniques is actually able to handle this imbalance and difficult sample scenario. Yeah, that's all. Those are some of my publications, and those are the references. Thank you, everyone.